Dear academicians and researchers, ladies and gentlemen, I am Artem Chamili, and it's my pleasure to be part of the 2022 workshop on computer methods in medicine and healthcare, which is itself part of the Transdisciplinary Information Sciences conferences. My talk today will be entitled A Toolkit for Secure and Private Machine Learning Disease Diagnosis in the Internet of Medical Things. Since I'm aware that some of our listeners of this talk might be non-IT guys, I'm going to give some informal definitions, or I'm going to go in depth with some technical details for which IT guys are aware of, but I think it's worth it. So let's get started. What is Internet of Medical Things? Well, for the IT guys, it's IoT, Internet of Things used for medical purposes, or Internet of Medical Things, or IoMT, is the collection of medical devices and applications that connect to healthcare IT systems through online computer networks. Now, what do we mean by classifying or diagnosing an unclassified query, or in IoMT, it's patient symptoms records? Well, I'm going to be a bit informal over here, namely, just like a human being, an expert of a certain health area is going to get his expertise or education. And after getting his expertise in, let's say, heart diseases or cancer diseases, etc., after getting the expertise, he's going to use that expertise to diagnose other patients. Similarly, a machine learning algorithm is going to train itself to get the trained model using patient records, which are basically consisted of patient symptoms with correct diagnosis for a certain disease. After a certain machine learning algorithm is going to see thousands, hundreds of thousands, maybe even millions of such records, it's going to be trained, and thus we have a trained model, and this trained model can be used to diagnose undiagnosed patients according to their symptoms. Okay, in this talk, we're not going to deal with the machine learning training. It's a topic for another talk, but I just want to emphasize that machine learning techniques often outperform the human experts in correct diagnosis. Let me give an example of IoMT using machine learning diagnosis. And I'm going to give an example of using multiple queries, multiple symptoms of multiple patients. Namely, let's assume we are at our home with our family members, and we kind of suspect whether we have COVID or not. So what we're going to do, we have wearable devices, if you wish. Those are computers on our body, which, let's say, measure our body temperature, pulse, heartbeats, other issues as well. And after constructing our symptoms for all of family members, we send those symptoms to a machine learning trained model to a certain clinic, and we get back results for all of us separately. This would be an example of IoMT using machine learning diagnosis. I want to also emphasize that several machine learning classification algorithms can be expressed through matrix operations, such as deep neural network, support vector machines, logistic regressions, flavors of Naïve Bayes, etc. And those matrix operations are dot or inner product, matrix vector product, matrix product, and so on. And we are going to see them in more details later on. So far, so good, but there is a drawback to this approach, and those are privacy concerns, namely laws, privacy regulation, and ethics. Because of those, we should not make patient records or their diagnosis public. Okay, to this end, from the patient perspective, including me also, I don't want my query or symptoms or my final diagnosis to be public, even for the clinic or the hospital. From the hospital or clinic or healthcare institution perspective, which has this machine learning trained model, well, it wants the privacy of the trained model. Why? Because it needed a lot of money and cost to train such a machine learning model, and it wants to get some revenue for it. If it makes it public, or if somehow it leaks the trained model, then no one is going to pay. Rather, they're going to use this trained model for free. So from the clinic perspective, we want the trained model to be private also. And while dealing with those IoMT disease diagnosis using machine learning, we want some other privacy and efficiency requirements. Namely, we want low computation and communication costs. This means when I'm going to take the results or diagnosis. I want to take it as soon as possible, which is low computation cost. And I don't want to send a lot of data through the internet, megabytes or gigabytes. I want to send small amount of data. Furthermore, I want it to be non-interactive. I just want to send my query symptoms and get the disease diagnosis back and not use multiple rounds. I want it to be resistant to quantum computer attacks because some privacy techniques can be attacked with quantum computers. As I already said, I wanted to use simultaneous diagnosis of more than one patient and many, many others. So let's get started. Naïve Bayes, we have a set of classes, and whenever I say classes, I mean diseases. So we have a set of diseases that we want to diagnose patients, and according to their feature values, okay? So, and furthermore, we have the probability of a certain class or disease to appear, and then we have a conditional class and feature value probabilities. And whenever I say feature, I mean symptoms. So basically here we have the probability if we observe a certain disease, what is the probability that the patient have that certain symptoms? We have all of them, and we have a query of patient symptoms, okay? So basically, what do we mean to classify or to diagnose a patient according to its symptoms? It means to assign the disease or class with a higher posterior probability to the patients according to his symptoms, okay? Namely, if we have F such feature values, then let me define the vector of class J or disease J, where J is from 1 to C, because we have C classes, in the following way. We'll put the probability of that disease in the first element of the vector, preceded by all of the feature values, conditional probabilities, class and feature value probabilities, or disease and symptom value probabilities. So this is for class J. If we do it for all classes, class 1, 2, 3, etc., then if we are going to have C rows with F+1 vectors, and this is my trained model for Naïve Bayes. Now, if I have a query which in its first element has 1, preceded by all of the indexes, preceded by slots or indexes for all the feature values, and if a certain symptom appears, I put 1 in this query. Otherwise, everything else is 0, and this is basically a column query. Then, according to Naïve Bayes, I'm going to classify or diagnose the symptoms by multiplying the trained model M with this query X. As a result, I'm going to get the resulting query vector, and I'm going to find the maximum element, which corresponds to the maximum posterior probability. As simple as that. This is for Naïve Bayes. For multinomial Bayes, again, you see this formula over here. Matrix vector multiplication and the maximum of the resulting vector. I'm just going to copy paste the same. Why? Because from multinomial Naïve Bayes, everything is the same. In this case, I have C diseases and F features or symptoms. And I'm going to define my trained model as a matrix, which in each row of it, it has the following. In the first element of that row, the probability of the disease, preceded by all of the conditional disease and symptoms probabilities, okay, for all of the C diseases or C classes. And basically, we're going to have, since we have F symptoms, we are going to have, and in the first index, we have the class probability, we're going to have a matrix with dimension C by F+1. Again, if I have a query, and here the queries, unlike in Naïve Bayes, where there are zeros and ones, here there are frequencies. Okay, so previously we might in Naïve Bayes, if a certain symptom appears, I'm going to have 1, otherwise 0. So if I have a heartbeat, let's say, I have 1, otherwise it's 0. But in multinomial Naïve Bayes, we don't see whether we have heartbeat or not, whether I'm dead or not, but I measure what is the heartbeat per minute. Let's say if it's 60, 70, I'm not going to put 1, but I'm going to put 60, 70, etc. So the difference is in multinomial Naïve Bayes, we put frequencies. In Naïve Bayes, we put either 0 or 1. But the classification is the same. Again, it's a matrix multiplication with a column vector, and I find the maximum of the resulting column matrix. Again, the same matrix over here. This is for support vector machines and logistic regression. I'm not going to go into details. Just I want to say that the trained model here in support vector machine are weights for each of the C classes or diseases, if you wish. And if I have a query vector like this with the symptoms, it's again multiplication of this matrix with query vector. And so you see all of those machine learning techniques in the end can be denoted and can be expressed in terms of matrix and query multiplication. The matrix is the trained model, and the difference between all of them is the way that we have found this matrix. As simple as this. If you remember, I told you I want to classify multiple queries for all of my family members. So instead of one query X, what if I have Q queries? Okay, and this is how they are given. And those Q queries are going to form my query matrix, which for each patient, I put in a column, not in a row, but in a column for the patients, the queries. Then, very simple, I can classify all of them in this way. Matrix multiplication. So this is my trained model, and these are the queries of my family members or Q patients. And if I want to classify simultaneously Q queries, okay, so I have the Q symptoms here, and I have the trained model. I just have matrix multiplication. And for each of the columns of the resulting matrix multiplication, I find the maximum element, and that's the classification for that corresponding patient out of Q patients. As simple as that. What about deep neural networks for non-IT guys? Well, let's see what is a neuron. A neuron is, in terms of IT, in IT terms, a neuron is a processing unit which takes one or multiple outputs, sums up those inputs, and it does some nonlinear function on it, which is called an activation function. Sigmoids, leaky reload, etc. And then it multiplies it with a weight and sends it to another neuron in the next layer. So basically, a deep neural neuron is consisted of, in this case, L+1 layers. In each layer, we have DL neurons, and all of the neurons have the same, in the same layer, have the same activation function, okay? And furthermore, those are connected with each other using weights. And the interesting part is that, let's say, layer L, and L, lowercase l, is from 1 to L, okay, because the input layer 0 is the input layer. And then we have L inner layers, thus in total L+1 layers. So if we take, let's say, this neuron over here, which is the second neuron of layer 1, okay, and all of the weights that goes from this neuron to another one, okay, then we have a vector. What if we put all of the weights of layer L, let's say? So the weights, which are links from one neuron to another one, okay, and basically each neuron of one layer is connected with each neuron of the neighboring layer by assigning some weights on that. And if in each column, starting from the first neuron, we put the layers of the first neuron of layer L, then the weights of the second neuron of layer L, which go to layer L+1, and so on. Then we have this matrix over here, which we're going to denote ML. Okay, so basically those are the weights. Those are the weights that I'm talking about. And since we have L+1 layer, thus L inner layers, we are going to have L such weight matrices, and basically all of those L weight matrices are going to be my trained model together with the activation functions for each layer. Now, if I have a query, which is shown here with the symptoms, okay, which basically goes to layer 0, then it's going to be multiplied by the weights, and then I'm going to apply some activation function. Well, it's given over here. This query here, the input query, is going to multiply by the first weight matrix, and then I'm going to have some activation for function. Then again, it's going to be done the same one. This is done L times. Okay. Well, Then I have the final classification. For multi-query is the same. Instead of X, we have XK. And again, instead of X, we have now, instead of one column vector, we are going to have now multiple queries, Q queries, and they are all formed of Q query vectors. So the classification will be done similarly. It's not going to be matrix vector multiplication, but it's going to be matrix multiplication, L multiplications from 1 to L, preceded by activation functions. As simple as that. Okay, so far so good. Now let's do a review of what we said so far. So imagine if we have one query, I live by my own at my home. I'm alone, let's say. Then I have one query, and I want to see whether I have COVID or not. So we have two classes: you have or not. So what if we merge those two raws for the trained model C1 and C2 by subtracting index-wise those? Well, then we are going to have the trained model one raw, and then for the query one raw. So basically, it's dot product. If it's greater than 0, I have the disease. Otherwise, I don't have it. Okay. So basically, we need to have secure dot or inner product. Why I say secure? Because I want to do it in privacy manner. But in order to do the dot product, we need secure sum. If I have C classes or C diseases in one query, then I have matrix vector product. And if I have Q queries, Q patients at my home, it's matrix product. Similarly, for deep neural networks, I'm going to have multiple cascading matrix operations, meaning one after another. And sometimes I need to do some secure matrix transpose. Furthermore, I want to do some permutation. So when I'm going to multiply, let's say, this matrix with the trained model matrix with the query, I want to permute the places of the resulting query of the resulting matrix vector product. Okay, and I want to find the maximum of that. But in order to find the maximum, I should compare all of them between each other. And also, I'm going to have some other intermediate operations. Well, that's why I need a toolkit for private operations. And this is the set of the operations that I'll need. And briefly, we'll go through all of them. So how are we going to get all of these secure toolkits? Well, it's in the core of our talk. This is how we're going to do it. Homomorphic encryption. We have 4 and 7. We want to encrypt them. What is encryption? Well, we have the secret key and the public key. Okay, basically, we encrypt it with one key and we can decrypt with the other key. And what is encryption? We take, let's say, an integer and we transform it using the secret key into something which is unintelligible, unrecognizable by us. So 4 is encrypted into this, 7 is encrypted into this. Okay, and if I make it public, no one doesn't know that this is 4 or this is 7. However, and this is basically encryption, and those unintelligible outputs of encryption are called ciphertexts. The interesting part about the homomorphic encryption is that if I add those ciphertexts, I'm going to get another ciphertext. But if I decrypt it, I'm going to get 11. And hey, 4 plus 7 is 11. So it works for addition. What about multiplication? So I'm multiplying those two. I'm getting, again, a ciphertext. But when I decrypt the ciphertext, I get 28. 4 multiplied by 7 is 28. So this is homomorphic encryption. We can do addition and multiplications on the ciphertext without having the need to decrypt them in the process. Furthermore, we can optimize this if we use a technique called Chinese remainder theorem. Namely, if in one ciphertext, instead of encrypting one, if we do some encoding, smart encoding, we can encrypt multiple integers. Let's say in A, I'm encrypting 5832. In B, I'm encrypting 2143. Then if I add A and B, A is one ciphertext, B is one ciphertext. If I add them, I'm actually adding component-wise, index-wise, their coefficients, if you will. So 5 plus 2 is 7, 8 plus 1 is 9, 3 and 4 is 7, and so on. So this is SIMD, single instruction multiple data. For multiplication, the same goes for addition, same goes for multiplication. Okay, if I use the Chinese remainder theorem. Now let's use some notations. So by MV, I'm denoting a vector of integers. If I encode it using the Chinese remainder theorem and encrypt them, then it's M underline C. But if I just encode it to be a plain text, and I'm with underline P, I have a plain text vector, and with underline C, I denote ciphertext. Of course, as we already saw, we can add them. We can multiply ciphertext between them. Ciphertext and plain text also can be added. And interesting, we have the rotation also. Basically, we already saw the addition and multiplication. Let's see what rotation is about. So let's say AC has encoded and encrypted those integers 5, 8, 3, etc. 2, 1. If I rotate it by 2 to the left, everything is going to be rotated. So you see 5, 8, 3 are on the first spot. But if I rotate it by 2, 5 comes to the third one, 8 comes to the fourth one, 3 over here, and 2, 1, which are in the end, go to the beginning. So I can do this while they are still encrypted. I can add, multiply, and rotate encrypted multiple integers. That's nice. Now, how I can use it with matrix operations? Now, let's say we have a matrix 2 by 2. I can encode them in 2 ways. Row-wise encoding, where I put the rows first, and column-wise encoding, where I put the columns first. When I put the rows, I'm going to use in the notation of the name with the variable subscript R. Otherwise, when I'm using column-wise encoding for matrices, it's going to be subscript C, uppercase C. It's shown 2 by 2, but you can generalize it for any dimensions. Secure sum. So how it works? That's a secure sum of blocks. So what's the input? Well, we have an input ciphertext with integers, and I want to find the sum of slots of D blocks, of blocks of D slots. Okay, what does that mean? So from here to here, I have D slots or elements. From here to here, I have D slots and so on. I want to find the sum of them. How I'm going to do it? So this is my input. I just rotate it by 1 to the left, you see. So A2 comes here, A3 here, etc. And I add index-wise. I add those two ciphertexts. A1 plus A2 is here. A3 plus A4 is here. Then this A3 plus A4 is kind of rotated to 2 to the left, and I add them. So here I'm going to have A1, A plus A2 plus A3 plus 4, and so on. Finally, I'm going to rotate it by 4 and add, by 8 and add, etc. In the end, I'm going to find the sum of these slots, as it's shown over here. I do it in log D additions and rotations. Ciphertext replication. Let's say we have a ciphertext, input ciphertext, C, underline C. We have these slots and everything else is 0. So these slots are not zeros. And with the replication rate is 4. So how am I going to do that? Well, again, I rotate the input ciphertext by D, and I get this one. Then I add those two. So how you see I have 2D now. Again, I rotate this by D, and I have 4D. So I've done this in log R, rotations and additions, and R is 4. So initially I have A1, A2, A3, A4. This is replicated by 4 times. This is ciphertext replication. Dimension replication. We have a ciphertext matrix encoded and encrypted. It has dimensions D1, D2, and we want to replicate the dimensions of the matrix. It's better illustrated in this figure over here. So we have 2 by 2 matrix. We want to replicate it. So D1, the number of rows is 2, the number of columns is 2. We want to replicate it by 4 times. What do we do? So A1, A2, we multiplied it with a ciphertext which has, so basically we take the first row, okay? And here is the result, only the first row. Then we take only the second row. Here is the result, A3 and A4. When I multiply it, and after the multiplication, I rotate it by 6, the output will come over here, okay? A3, A4. Now, I add those two, A1, A2, A3, A4. This is what I'm going to get. And here I use the ciphertext replication technique that we just explained to get this one. Now you see, first row is replicated by 4 times, and the second row is also multiplied by 4 times. Why do we need that? We're going to see it. Let's see how do we do the secure dot product in a product. Basically, if I take 2 vectors with dimensions D, I just multiply them and then use the secure sum to find them. So this is dot product, inner product. Let's see how we're going to use the secure sum protocol that we just explained to find their dot product. What about matrix vector multiplication? Well, that means the vector should be multiplied with all of the rows. So that's why I'm going to replicate the vector with the number of rows of the matrix, and then I'm going just to find the secure dot product of those two. Matrix multiplication, interesting part. we have one row encoded matrix, ciphertext, another ciphertext of column encoded matrix, and their dimensions are D1 by D2 and D2 by D3 correspondingly. I want to find their matrix multiplication. Let's see it with an illustration. So this is my matrix, row encoded, A1, A2, A3, A4. The second one is column encoded. So what do? For the first matrix, the row encoded, we use the ciphertext replication technique to replicate it by 2. So we have A1, A2, A3, A4. After replication, this is what we get. The second one, we replicate the dimensions of it using secure dimension replication. So we have B1, B2, B3, B4. After replicating the dimensions, you see B1, B2, B1, B2 is replicated 2 times. Then B3, B4 also is replicated 2 times. Then we just use the dot product of those 2 to get the resulting matrix, which is shown over here. Okay, this is the matrix that we're talking about. Okay, so basically all D1, D2, D3 multiplications are done with a single SIMD homomorphic multiplication. You might say there's a problem. Why do we have zeros here? Yes, this is sparsely encoded matrix. That's why we want to compress to remove those zeros. So remember this. And how do we compress it? Well, this is how it's shown. So we have number of blocks is 4, block size is 1. These the empty data slots between the elements. So how do we do it? Well, it's shown here, A1, A2, A3, A4. I rotate it, I add it. Then I multiply it with this plain text and I get A1, A2, A3, A4. Then so the number of blocks is that we have 1, 2, 3, 4 elements. The block size is each of those blocks has 1 element. And now after the first rotation addition, you see, we have now 2 blocks, 1 and 2, but they have 2 elements, okay? That's why I rotate by 2, and this is what I get. And finally, when I multiply it by 1, I get A1, A2, A3, A4, which is A1, A2, A3, A4. So this sparsely encoded matrix is kind of compressed, right? What about, so let's go back to this slide over here. So how we are going to compress this? Well, we are going to see it. It should be obvious right now. If you want to just multiply 2 matrices using secure matrix protocol, we saw that they are sparsely encoded. Well, in order to compress them, we use theccompress matrix function or protocol if you wish, and they are compressed. So basically, you see, remember for the matrix operation, this one that we just completed, we use C replication for the first matrix, secure dimension replication, the secure dot product to get this one. And then we use the ccompress to get this matrix, which is the column-wise encryption of the resulting matrix. You might say, what if I want it in row-wise encryption? Well, then you should transpose it. And here we have the secure matrix transport protocol. It's illustrated in this figure over here. I'm not going to go into details because of time. So basically, my input is this one. We do some operations in order to get the transpose matrix. It's shown by 2 by 2 dimensions, but you can just generalize it by D1 by D2 dimensions. Okay, we have also ciphertext permutation. Basically, if we have blocks of slots and I want, so here we have like M is 3. So we have in one block, we have 3 data sets that we are concerned of, and we want to permute them inside of that block. So basically, we want A1 to go here, A2 here, A2. That's here. A1 goes 2 slots to the right, A2 goes 1 slot to the left, A3 goes 1 slot to the left, and it's done in SIMD fashion. This is how it's done. It's shown in details with this illustration over here. We don't have time, but this is how we permute inside of the blocks data slots. What about secure comparison? Well, I just simply do A1 minus B. So this is one ciphertext, another one. I just subtract the first 2. I add a random R such that it's greater than 0. And then I multiplied A1 minus B with a random R, and random R is greater than 0. And I just add an H such that the absolute value of H is smaller than R. If the final term is positive, that means that A is greater than B, and vice versa. So this is to compare just, index-wise those data. But what if I want to compare not only A1 and A1, B1, but I want to compare all of those guys between them? Well, this is how we do it. So we have A1, A2 up until AC. I want to compare those with each other. How do I do it? Well, I just shift it to the right, the first ciphertext, and I subtract it. So I get A1 minus A2, A2 minus A3, etc. Then I shift it again. So here I get A1 minus A3, A2 minus A4, A3, etc. And finally, I add all of those up, and this is what I get: A1 minus A3, A1 minus A2, etc. So basically, it's a subtraction of all the possible combinations. Now to this, I add R and H in the way that I described in secure comparison. And finally, here I have the secure comparisons for A, for A2, and for AC, which is the maximum. The maximum of all A1 through AC is the one that has all of the comparison results greater than 0. Finally, we go to what we came from here, how we can do secure and private machine learning query classification, multi-query classification for multiple patients. Well, we have a clinic, which is a server basically, and it has a trained model, and it has a private decryption key, okay? And we have patient, which is the client, and the clients have multiple queries that they wish to classify in privacy-preserving manner. The server and the clients are in the semi-honest model. This is for the crypto guys out there, which means that they follow the protocol, but on the background, they try to infer some data. So what do we do? Let us remind us of this formula. Trained model multiplied by the query model, this one. So those are the patients, wearable devices. They collect temperature, heartbeats, pulse, whatever, blood pressure, whatever. And they construct those queries Q1, step 1. In step 2, they kind of construct them in a matrix form, S. So they form S, this one. In step 3, we need to do, okay, so step 1 is given from 1 to 3. Step 4 is given in step 2 here, where we construct C is given here. In step 5, we do the secure matrix multiplication. Then we continue with secure comparison of all data slots, but which we explained, and we permute the places of them. Okay, this is in step 4 over here. Then finally, we send it to the server, which is going to decrypt, and for each patient, it's going to find the maximum of the result, but the maximum is kind of permuted, right? And send those permuted maximums to the clients, and the client is going to do the inverse ciphertext permutation to find the final result. This is how we do it. But this is for those that have one matrix operations. What about deep neural networks? Well, then instead of line 5, just a kind of reminder, then instead of this operation, we're going to have L matrix operations preceded by activations. Okay, so basically line 5 is going to be substituted with those 7 lines where you see from 1 to L, we use secure matrix cascading operations, right? Well, this is it. Now just experimental evaluations. We evaluate our secure toolset with Wisconsin breast cancer and acute inflammation data sets, and we get pretty good results, which we compare with the state of the art, and we beat them. And so this is the privacy preserving Naïve Bayes for the Wisconsin breast cancer. We beat them. Logistic regressions for Wisconsin breast cancer data set with the state of the art schemes. We beat them in computation, communication cost. Similarly, for the logistic regression, we also beat them. If you see here, I'm using other data sets, not only health, like cybersecurity, or here I'm using SMS spam datasets, because the proposed toolkit set is not only applicable to health, but to other areas like finances or cybersecurity, etc. This is also for acute inflammation datasets, and our theoretical analysis so that they are secure under the semi-honest model, which we just explained. Okay, well, that would be all. Thank you for your attention, and I can have your questions right now.